All right, hi folks. So this is for those of you who were not present during the Zoom session on Monday, or if you were asleep during the Zoom session on Monday. This is an example on how to write beta decay equations, electron capture equations, and positron emission equations. So this is the example we went over in class. It says iodine 131 is sometimes used as a treatment to treat thyroid disorders. A solution of iodine 131 is mixed into a beverage and ingested by the patient. Iodine is needed in the production of thyroid hormones, so the thyroid readily incorporates the radioactive isotope. Beta radiation is released and the thyroid is destroyed. And then we're going to write the beta decay equation for the decay of iodine 131. So the first thing we need to do is we need to look up the symbol and atomic number for iodine. I can do that by pulling up my periodic table and find iodine just like this. Its symbol I and has an atomic number of 53. So I write I 53 and it has a mass number 131. Now, beta decay means that there is an electron that is being released out of the nucleus of this radioactive isotope. And I can model that if you look at my webcam quickly. Here's a neutron. A neutron is essentially a proton and electron combined together in terms of mass. And if I remove that electron, I am left with a proton. Proton's a larger piece, the smaller piece is the electron. And then you can see that electron capture would be when the electron is sucked into a proton and re-becomes a neutron. So electron decay, beta capture. So I need to figure out what daughter isotope will be left after an electron has left the nucleus of iodine 131. So I say to myself, what subtracted 1 by it will end up the answer 53. And the answer there is going to be 54. So 54 minus 1 is 53. It's kind of looking at a math equation backwards. And so I can do the same thing with my mass, except I know that the mass number doesn't change with beta decay. Last step is I look up on my periodic table what the symbol is for element 54, and I find that that's xenon. And this is going to be the example of how to write a beta decay equation. Let's now look at what a positron is. So there are bazillions of different types of subatomic particles that we're just going to just scratch the surface of. But one different type of subatomic particle that you might not have heard of before is a positron. And a positron is a particle that's the same size of an electron, but it has a positive charge. And we symbolize that with an E because it's the size of an electron. It essentially has no mass, and it has a positive 1 charge. We're going to write a positron emission equation for silver 110. Now, in terms of the word emission, when I see that, it means that the positron is leaving. So I know that the positron will be on the right side of the equation. So I start again looking up my symbol for silver, which is right here. Silver has an atomic number of 47 and a symbol of Ag. The problem told me that it has a mass number of 110. And again, since it's spitting out a positron, the positron goes on the right side of the equation. Now, I have to figure out what number added to 1 makes 47, and that's going to be 46. 46 plus 1 is 47. And just like with beta decay, the mass still doesn't change here, and I will have a mass of 110. I have to look up on my periodic table what the symbol for atomic number 46, and I will find its palladium, symbol PD. And I have that written there just like that. So if I say positron emission, I have a positive electron that will have left the parent isotope to make a daughter isotope, which has an atomic number 1 less than what I started. Last, electron capture. So electron capture can also be called beta capture, and it's kind of like alpha capture, that the parent is sucking in that beta particle rather than spitting it out. And we're going to do this for platinum 190. So looking at my periodic table, platinum is right here. It's number 78. It has a mass of 190. And this time I'm going to be adding to this, and my T's and my pluses look so much the same. Let me fix that really fast. That is going to be T plus an electron. And I'm going to take 1 away from the 78 to make 77, take 0 away from the 190 to make 190. So what I will be left with for a daughter isotope has a mass of 190, has atomic number 77, and we can identify that as iridium number 77 right there on your periodic table. Now notice with electron capture, your atomic number decreased by 1, and with your positron emission, the same thing happens. Your atomic number decreases by 1. So for all essential purposes, the end product of positron emission and for beta capture are the exact same thing. You'll still end up with the same thing. It's just a different type of particle making it happen. So this is the review that we went over in the Zoom session on Monday, March 29th, and hopefully this will help you complete the worksheet.